Tonight, we're going to dive into the truly wild world of black holes. These aren't just the weirdest things out there in the cosmos. They actually offer us the sharpest tests for understanding how reality itself functions. They come into being when a huge amount of mass gets squished down past a certain crucial point. But their importance goes way beyond just how they're made. Black holes are like the ultimate extreme labs in the universe. They force general relativity and quantum mechanics to clash head-on. In this extended journey, we're taking a look back through years of discoveries to spend some time exploring how these incredible objects form, how they change over time, and ultimately, how they help us put our deepest ideas about reality to the test, and maybe even bring them together. So, before you get comfortable, take a moment to like the video and subscribe. Let me know in the comments where you are in the world and what time it is for you. Black holes stand out as some of the most peculiar entities we know of in the entire universe. To even begin to imagine making one, we need to bring together both general relativity and quantum mechanics. We'll explore exactly how that happens. Previously, we've discussed what black holes truly are. We've talked about them as structures described by general relativity, as specific areas of space-time where the boundary's curvature essentially cuts off the inside from anything we can observe in our universe. Now, it's a good idea to watch that earlier discussion if you haven't already. These are some pretty abstract concepts, and honestly, black holes were initially just a strange outcome of general relativity's equations. Just because something appears in the math doesn't automatically mean it has to exist in the real world. So, are black holes actually real? The answer is a definite yes. Black holes are confirmed astrophysical objects, and we have a ton of evidence supporting their existence. However, to actually bring a black hole into being, Einstein's explanations of mass, energy, and space-time aren't quite enough. We also need quantum mechanics. If you're up for it, let's try to construct a black hole ourselves. Our first step is to locate a truly massive star and then simply wait. Just let it do its thing, but not for too long, because these colossal stars have incredibly short lifespans. We're talking only a few million years until their dramatic supernova explosion. If you're feeling a bit impatient, you could theoretically crank up the core temperature by hitting it with gravitational waves, which would speed up the process. The specifics of how massive stars end their lives are actually quite spectacular, but that information is readily available in many places, so we'll just briefly touch upon it here. In the final, most intense stages of a very massive star's existence, increasingly rapid nuclear fusion inside its core produces one element after another. These elements arrange themselves in layers, like a set of Russian dolls, with progressively heavier atomic nuclei forming concentric shells until eventually an iron core takes shape at the very center. The creation of that iron core signals the end of fusion reactions that release energy. When you try to fuse two iron nuclei, it actually takes energy. It doesn't give any off. So, with its primary energy source gone, the star's core begins to collapse inward under its own immense gravity. Electrons are violently forced into protons within the iron nuclei, creating a neutron star. The star's outer layers, collapsing at incredible speeds, then bounce off this unbelievably dense, newly formed nugget in a spectacular supernova explosion, scattering freshly made elements across the galaxy. This enriches the cosmic environment with new building blocks. The remnant core, this neutron star, is an incredibly bizarre entity. It's a ball of neutrons, roughly the size of a typical city, yet it holds the mass of at least 1.4 suns, and its density is comparable to that of an atomic nucleus. We often spot these objects when they appear as pulsars, rapidly rotating neutron stars that emit beams of radiation. Below a thin layer of iron plasma, A neutron star is fundamentally a quantum mechanical object. It's a specific quantum phenomenon that, for a brief time, saves it from a complete, final collapse. Interestingly, it's also a different quantum phenomenon that will allow us to push it past that edge, ultimately forming a black hole. To grasp how space works for a quantum entity like this, we need to consider not our familiar three-dimensional space, or even four-dimensional spacetime, but rather a six-dimensional quantum phase space. For a neutron star, this refers to the space that includes both its three-dimensional position and its three-dimensional momentum. This defines the total volume that can be occupied by the exotic matter within the neutron star. Now, the precise way the matter of a neutron star fills this six-dimensional quantum phase space depends on two crucial principles from quantum theory: the Pauli exclusion principle and the Heisenberg uncertainty principle. These two principles maintain a delicate balance between the star's stability and its ultimate gravitational collapse. The Pauli exclusion principle essentially states that two identical particles, or fermions, cannot occupy the exact same quantum state at the same time. By thing, we mean fermions, which are the type of particles that make up all ordinary matter, such as electrons, protons, and neutrons. By place, we mean a specific location in quantum phase space. So, two fermions can perfectly well occupy the same physical location in space, as long as their momenta, or any other quantum property, are different. This fundamental rule is what keeps electrons in their distinct, stable orbits around an atom, and in turn, it's part of what gives solid matter its structure and rigidity. In the extreme case of a neutron star, its position momentum phase space is entirely packed with neutrons. Every single spatial location and every corresponding momentum location linked to those spatial points is filled by a neutron. Now, a bit of jargon here: this unusual state of matter, where phase space is completely full, is what we call degenerate matter. And the pressure that arises from this degeneracy, a pressure created because particles literally have nowhere else to be compressed into, is incredibly powerful. It's strong enough, at least initially, to resist the overwhelming gravitational crush of a neutron star. As far as we currently understand, there's no direct way to bypass the Pauli exclusion principle. You see, it's not a matter of applying more force. Two fermions simply cannot, ever, occupy the same quantum state. It's a fundamental rule. So, for a while, the neutron star remains stable and safe. But hold on, we're trying to build a black hole here. Fortunately, there's another quantum phenomenon that offers us a way around the strictures of the Pauli exclusion principle. The Heisenberg uncertainty principle tells us that the properties of any quantum entity are fundamentally uncertain. The intricate details of this might be a subject for another discussion, but in simple terms, quantum mechanics describes matter not as distinct points, but as a distribution of possibilities. Specific numerical properties you can assign to a particle exist as a wave, embodying varying degrees of maybe. Location is one such property. A neutron, for instance, isn't in one specific place, but rather exists as a cloud of potential locations. This cloud might be very tightly confined or quite spread out. A neutron's location remains this cloud of possibilities until it interacts with another particle, at which point its position becomes resolved. This is one of the most astonishing and cool aspects of quantum mechanics, and we'll hopefully delve deeper into it another time. But for now, we have a black hole to create. The Heisenberg uncertainty principle states that certain pairs of quantities, specifically position and momentum, or time and energy, must, when considered together, possess a minimum degree of inherent uncertainty. If one of these quantities is very tightly constrained, then the other must be highly uncertain, spanning a wide range of potential values. So, a neutron star is made of the densest matter in the entire universe. Its individual neutrons are packed together as closely in position as physically possible. Therefore, the Heisenberg uncertainty principle dictates that they must have incredibly ill-defined momenta. This means that very, very high neutron velocities become a part of the realm of possibilities. To put it differently, the neutrons are crammed so tightly together in position space that their momentum space becomes enormous. The overall phase space expands. And here's the crucial point: the denser the neutron star becomes, the more momentum space it gains. So, Heisenberg's principle allows us to get around that stubborn degeneracy pressure. If we can somehow add more matter to a neutron star, perhaps by flinging another star at it, it won't necessarily get physically larger in space. The additional matter certainly needs somewhere to exist. You'd think the star would have to expand. But it doesn't expand in position space. Instead, the star expands in momentum space. In actual physical position, it actually shrinks. The more massive a neutron star becomes, the smaller its physical radius. This is a purely quantum effect, even though it's happening on the scale of an entire star. Up until this point, the neutron star has managed to remain just above a critical size. The curvature of spacetime at the surface of a neutron star is already pretty extreme. Clocks there tick noticeably slower, and the incredibly high densities within the star create some truly exotic states of matter. However, despite all this, the star is still very much a distinct object within our universe. Yet, just beneath the star's surface, the potential for an event horizon lurks. This would be the surface where time dilation becomes infinite. Now, this event horizon doesn't actually come into existence as long as the neutron star's physical size remains larger than this hypothetical horizon. However, if we can increase the mass of the neutron star, the actual star itself shrinks, and at the same time, the potential event horizon expands. You can probably see where this is heading. There's a specific mass where the radius of the neutron star and the radius of the event horizon perfectly overlap. This critical mass is approximately 3 times the mass of our Sun. At this precise point, the event horizon truly materializes, and the neutron star is swallowed, submerging beneath it. We have finally succeeded in creating our black hole. But what actually happens to the star once it slips below its own event horizon? Everything inside that boundary is irrevocably lost from our observable universe. Spacetime within the newly formed black hole is radically transformed, with all geodesic paths, the natural trajectories objects follow in spacetime, turning inward, directly towards the center. When the black hole first forms, the material inside must still resemble the dense stuff that made up the original neutron star. However, there's no stopping the ultimate collapse. All paths inevitably lead to the central point of infinite curvature, which we call the singularity. From the perspective of the star itself, this inward cascade happens. All of its position space collapses relentlessly towards the singularity, while its momentum space expands correspondingly, with all the resulting enormous velocities pointing relentlessly inward. The neutrons within are certainly ripped apart into their fundamental components, quarks and gluons. But what happens to these particles as the star approaches an infinitesimally small point, reaching the Planck scale? Our current understanding of physics simply cannot tell us yet. From the viewpoint of an observer outside the black hole, that's us. This complete collapse never actually appears to happen. The black hole forms, and the stellar core simply goes dark. But on our timeline, nothing ever appears to cross the event horizon again. We can't meaningfully consider what's happening, beneath the event horizon. There is no corresponding for events inside relative to our outside timeline. The material of the star, and all events that occur to it, are no longer part of the timeline of the external universe. According to our clocks, the singularity would form infinitely far into our future. To us, only the event horizon truly exists. So, this is how a real, astrophysical black hole is created. The mass of the stellar core becomes the apparent mass of the black hole, and very few other properties of the collapsed material are remembered by the outside universe. The black hole retains its mass, its electric charge, and its spin, and these properties continue to influence the universe around it, sometimes in incredibly significant ways. Of course, a real black hole isn't the unchanging, static entity we sometimes describe in theoretical models. They grow, they emit radiation, and they change. We'll delve into what this means for black holes and for the universe itself in a future discussion. In the very first moments, immediately following the Big Bang, the density of matter was so extraordinarily high everywhere that it's possible vast numbers of black holes could have formed. These hypothetical primordial black holes might still be present in our universe today. There's no longer any doubt that black holes exist. The recent observations by LIGO detecting gravitational waves from merging black holes provided stunning confirmation of this fact. Of course, we already strongly suspected their existence, given that general relativity tells us a black hole will form whenever a volume of space contains a sufficiently high density of mass or energy. In the modern universe, there's only one natural process that can create such extreme densities, the core of the most massive stars as they reach the end of their lives. The detailed process is fascinating, and we've explored it in a previous video, but that describes the modern universe. Once upon a time, however, the entire universe had a density comparable to that of a collapsed stellar corpse. In fact, very soon after the Big Bang, the universe's density was astronomically higher. So, why didn't all the matter in the universe immediately turn into black holes back then? Well, it's possible some of it did, forming what we call primordial black holes, and they might still be lurking around today. Let's take a step back for a moment. To create a black hole, extremely high density alone isn't quite enough. You also need a density differential. Without variations, there's no preferred direction for all that gravitational attraction to pull towards. Additionally, the gravitational pull needs to be powerful enough to overcome the rapid expansion of the universe. Now, matter in the very early universe was actually spread out quite smoothly, and the universe was expanding at an incredible rate. This meant that most of it avoided collapsing into black holes. And that, by the way, is a very good thing for us. However, the early universe wasn't perfectly smooth. There were tiny lumps and irregularities. The oldest light we can possibly detect is the cosmic microwave background radiation. This ancient light reveals minuscule differences in the density of matter from one point in space to another. The universe was very slightly lumpy at the moment the CMB was created, approximately 400,000 years after the Big Bang. These density fluctuations were sufficient to kickstart the formation of galaxies over vast timescales, but certainly not strong enough to immediately collapse into black holes. Yet, if we mentally rewind time even further, those fluctuations must have been much more pronounced. It's theorized that these fluctuations originally arose when the entire observable universe was smaller than a single atom. Back then, quantum fluctuations caused a kind of static fuzz across the minuscule cosmos. There are several different theoretical explanations for the initial size and subsequent growth of these fluctuations, and cosmic inflation certainly plays a significant role. However, it falls well within the realm of possibility for many models that some of these fluctuations were, at certain points in the early expansion, intense enough to resist the local expansion of the universe and form black holes. Some highly speculative theories related to the Big Bang also predict the existence of primordial black holes. For example, they could have formed from the collapse of cosmic string loops, or even from the collision of bubble universes. Pretty awesome stuff. These models can predict an enormous range of possible masses for primordial black holes, or PBHs, as they're often called in the field. PBHs could have been formed with masses ranging from just a few grams to tens of thousands of times the mass of the Sun, depending on which specific formation model you consider. Or it's entirely possible they don't exist at all. That's a significant possibility. If they do exist, then there's likely a particular mass range where most of them would have formed. Discovering PBHs and determining their masses would tell us an immense amount about the very first moments of our universe. We need to actively search for these black holes, or at least their gravitational influence, in the modern universe. First off, we're not going to find primordial black holes weighing less than about 1 billion tons, which is roughly the mass of a small asteroid. Any such smaller PBHs would have completely evaporated away by now due to something called Hawking radiation. We'll come back to that concept. Black holes larger than this minimum size should still be around, but they would be incredibly challenging to spot, being so, well, black and all. If PBHs are truly rare, then it might be impossible to definitively confirm or disprove their existence. However, there's one question we can address with some degree of certainty. Could primordial black holes actually be dark matter? This is a slightly unsettling possibility, suggesting that 80% of the mass in the universe is made up of countless swarming black holes. That would be an enormous number of primordial black holes. If this were the case, we would expect them to leave their signature on the universe in various ways. For one thing, if these tiny knots of warped spacetime are everywhere, then they should produce noticeable gravitational lensing effects. We would expect them to frequently pass in front of other cosmic objects. Depending on the PBH's mass, this would cause a twinkling effect known as microlensing in stars within our own galaxy, in distant quasars, and even in gamma-ray bursts. And, honestly, we just don't observe enough of this twinkling, which effectively rules out a large portion of the possible mass ranges for PBHs as dark matter. There's also the fact that vast swarms of black holes would significantly disrupt their surroundings. As the heavier ones zipped around the galaxy, they should tear apart loosely bound binary star systems and have a noticeable impact on the structure of star clusters. The smallest ones should fall into neutron stars, causing those neutron stars to either explode or transform into black holes themselves. But we do observe plenty of loosely bound binary systems, normal star clusters, and an abundance of neutron stars. These arguments allow us to rule out all, but a very narrow set of mass ranges for primordial black holes as an explanation for dark matter. The remaining options we are left with are either a huge number of PBHs with masses similar to a large asteroid, like Ceres, so roughly 10 to the 21st power kilograms, or a much smaller quantity of truly enormous PBHs, around 20 to 100 times the mass of the Sun. Now, this latter possibility is a bit more speculative. Some scientists believe that the ravenous feeding habits of many really big primordial black holes would have left an observable imprint on the cosmic microwave background. However, other researchers argue that the recent detection by LIGO of two approximately 30 solar mass black holes merging could be evidence supporting this idea. With new observations from both conventional telescopes and LIGO, we are rapidly closing all of these potential mass windows. Before too long, we will either definitively spot the signature of primordial black holes within these specific mass ranges or discover that PBHs are, in fact, exceedingly rare and certainly not the elusive dark matter. The latter outcome seems more probable, but time will tell. Of course, primordial black holes that have already evaporated due to Hawking radiation definitely cannot be dark matter, and that rules out any PBHs lighter than approximately 1 billion tons. But that final stage of Hawking evaporation is incredibly fast. In fact, it's explosive. It's conceivable that certain types of very short gamma ray bursts are these final, brilliant flashes from PBHs evaporating in our own galaxy. This is highly speculative territory, but it presents some truly exciting possibilities. It wouldn't be right to conclude a discussion on primordial black holes without considering what might happen if one were to pass through our solar system. Even a close encounter with a black hole as massive as the Sun or larger would be quite devastating. If it passed anywhere near the planetary system, its immense gravitational pull would severely disrupt the orbits of our planets. Even if it merely grazed the outer regions of the solar system, it could still shake up the Oort cloud, potentially sending a significant shower of comets to bombard the inner solar system. Of course, regular black holes, those formed from supernovae, could and perhaps have already caused similar events. Having a large number of high-mass primordial black holes would simply make such occurrences more likely. If PBHs are closer to the mass of a large asteroid, then they are too low in mass and probably moving too fast to inflict any significant gravitational damage. They would likely just zip right through the solar system completely unnoticed. It's a different situation, though. If one were to actually strike Earth while traveling at a couple hundred kilometers per second, it would punch straight through our planet, leaving behind a narrow column of vaporized rock. These kinds of impacts would be incredibly rare and might never actually happen. However, if primordial black holes have approximately the minimum possible mass to avoid having evaporated, around 1 billion tons, these would be much more abundant than asteroid mass PBHs. In fact, they might pass through our planet quite frequently. A 1 billion-ton black hole has an event horizon roughly the size of a proton. So, it would pass through Earth as if our planet were made of air, barely interacting. However, it would deposit something like 1 billion joules of Hawking radiation on its journey through. This should leave detectable traces in crystalline material within Earth's crust. In fact, perhaps geologists will be the first to actually discover primordial black holes. If they are out there, someone will certainly figure it out. I mean, how long can the universe really expect to conceal vast numbers of holes punched right through the fabric of space-time? The singularity, that point of infinite density at the very core of a black hole, is also so much more. In the realm of mathematics, singularities come in an incredible array of wild and wonderful varieties. The black hole itself, in fact, contains more than just one. Isaac Newton's universal law of gravitation was an extraordinary insight when he first formulated it in the late 1600s. Indeed, we still rely on it to guide spacecraft around our solar system today. However, it does have its limitations and problems. Let's briefly look at the mathematics. Newton's equation calculates the gravitational force exerted between two masses, m1 and m2, separated by a distance r simple enough, but that r squared term in the denominator spells trouble. It means the gravitational force becomes much stronger the closer the masses are to each other, which makes intuitive sense. But what happens when it gets extremely close to zero? At that point, the result of the equation, the force, becomes astronomically large, and it becomes infinite precisely when r is equal to zero. That doesn't really make a lot of sense. Infinite force implies infinite acceleration, which means, well, physics simply breaks down. According to Newton's law, to experience that infinite gravitational acceleration, you would need to reach zero distance from an object's center of mass. This implies that all of that object's mass would have to be concentrated at that single central point, a point of zero size. That, of course, would mean infinite density, which is exactly what we call a black hole. We often use the word singularity to describe the hypothetical, infinitely dense core of a black hole. But in mathematics, the meaning of this word is far more general. You know what? Instead of me trying to explain mathematical singularities, how about we get an actual mathematician to do this properly? Folks, meet Kelsey Houston Edwards from the PBS show Infinite Series. Hey, Kelsey. Hey, Matt. Thanks for having me on. Kelsey, the math for black holes often goes to infinity for different properties and in different locations. What does all this mathematical weirdness actually tell us? Well, mathematicians use the word singularity pretty broadly. It's really just any point that causes problems in an equation. Commonly, these problematic points are where quantities become larger and larger, approaching infinity, just as they do near a black hole. Some singularities arise purely from your choice of reference frame or coordinate system. An example of a frame-dependent singularity that might be familiar to those who watch spacetime is the event horizon of a black hole. I'll let you explain that one. Here on Earth, the North and South poles are examples of what we call coordinate singularities. It's mathematically possible to pass through time zones infinitely quickly at the poles. But that's only because of your choice of spherical coordinates, not due to any physical weirdness. Alright, that makes sense. But the gravitational singularity at the center of a black hole is what's called a real singularity, right? I mean, the curvature and the density are infinite from any frame of reference, correct? And there's no way to escape a horrible crushing death just by switching coordinate systems. But the very reality of the black hole singularity might give us reason to question the theory that predicts such a thing. In fact, this has happened many times before in the history of science. From models of water movement to predictions of human population growth, mathematics has predicted a physical singularity, and we've subsequently been forced to reject the corresponding theory as incomplete. So, are you saying Einstein is wrong? Blasphemy. Actually, Einstein himself agreed on this point. Folks, you really should check out Kelsey's show, Infinite Series, where she delves much deeper into the nature of singularities. It's a math show, by the way, so it's sometimes about real physical things. Mathematicians are lucky. Being constrained by reality can be so dull. So, does the fact that it includes a singularity mean there's something fundamentally wrong with Newton's law of gravitation? Well, we already know that Newton's law isn't truly universal. When the gravitational field is too intense, say near a star or a black hole, Newton's law gives incorrect answers, and we need Einstein's general theory of relativity, which is a far more complete theory of gravity. So, does general relativity get rid of Newton's troublesome singularity? No. In fact, it gives us even more singularities. To understand this, we need to examine something called the Schwarzschild metric. This is what you get when you solve the delightfully complex Einstein field equations for the simplest possible case: a spherically symmetric mass existing in an otherwise empty universe. We're going to simplify it even further to only allow movement directly towards or away from our massive object. In that specific case, the equation looks like this. Okay, that certainly looks like some serious math. Hey, this is spacetime, we can handle it. Actually, it's quite straightforward to spot the singularities in this equation. But let me first walk you through what it's telling us. The Schwarzschild metric allows us to compare 2 points, or events, in spacetime around a massive object from the perspective of different observers. For example, a short spacetime path of some object, its world line, might involve the object moving a distance delta r over a short time step delta t. This motion is either towards or away from the massive object, which is itself at a distance or away. That delta squared term represents the spacetime interval, and it's a very strange and interesting quantity. Every inertial, meaning non-accelerating, observer will agree on the same spacetime interval for every pair of events and for every world line. We discuss this in much more detail in our relativity playlist. Today, we'll keep it simple. As long as our object's world line doesn't require faster than light motion, then the square root of the space-time interval is equal to the amount of time that the object itself experiences over that interval. We call that the object's proper time. Oh, and subscript is a measure of the mass of the massive object. In fact, it's 2 times the gravitational constant multiplied by the mass. There would typically be some speed of light terms in the equation, but we've set them equal to 1 because, well, we're that cool. Now, the first thing to notice is that the singularity is still present in the Schwarzschild metric. The variable representing the distance to the center of mass remains in the denominator, just as it was in Newton's law. When you use the Schwarzschild metric to calculate the curvature at r equals 0, that curvature is infinite. This gives us the same infinite gravitational pull as the Newtonian singularity. And just as with the Newtonian case, this gravitational singularity can only exist if infinite densities are physically possible. But unlike Newton's law of gravity, the Schwarzschild metric actually hints at whether or not that infinite density is expected. To understand how, we need to look at the second singularity in this equation, a singularity that Newton's law does not contain. You see, when the distance to the center of mass, or is exactly equal to this rs term, then rs over r equals 1. At that point, the entire equation starts behaving very badly. It's as much a mathematical singularity as the one at the center of the black hole. If you haven't guessed already, this problematic behavior corresponds to the event horizon, and rs is the Schwarzschild radius. Imagine an object sitting precisely at the event horizon but not moving. So, its delta r would be 0. But that bracketed term is also 0 because 1 minus 1 equals 0. The entire spacetime interval for a non-moving point at the event horizon is 0. But remember, for sublight speed world lines, the spacetime interval tells us the rate of flow of proper time. So, does that mean time doesn't pass for an object hovering at the event horizon? Not exactly. Time certainly doesn't pass at the event horizon. No clock ticks can ever occur there. But the prohibition against objects experiencing time at the event horizon is actually a prohibition against objects spending time at the event horizon. No temporal entity, nothing that normally experiences the passage of time, can have a spacetime interval of 0 while remaining stationary. At the event horizon, the only way to achieve a non-zero spacetime interval is to have a non-zero delta r. An object at the event horizon has to change its distance from the black hole to keep its clock ticking. That means falling below the event horizon. And once inside, inward spatial movement continues to be the only way to fuel the ticking of an object's proper time clock. We'll return to that bit of amazing strangeness in a future episode. There is one thing that can have a spacetime interval of 0 light. Actually, anything capable of traveling at the speed of light can only have a spacetime interval of 0. From its perspective, a photon exists in a single instant, and so it can, in a sense, hang out at the event horizon, which also exists for one infinitely stretched out instant. The act of crossing the event horizon is where this coordinate singularity truly starts to behave erratically. At the exact moment of crossing, the denominator in the Schwarzschild metric becomes 0, and the entire equation blows up to infinity. But what is actually infinite here? It's nothing physical. It's the fact that even an outgoing light ray would take an infinite amount of time to move any observable distance from an outside perspective. So, using our ordinary concepts of time and distance, delta t and delta r simply doesn't allow us to smoothly trace a world line across the event horizon. That horizon is what Kelsey called a coordinate singularity. But this means we can fix it. There are specific ways to construct our spacetime axes so that this particular singularity simply vanishes. For example, Eddington, Finkelstein coordinates teach us how to compactify the coordinates, essentially accounting for the stretching of spacetime to cancel out these infinities. That's a bit much for right now, but feel free to search for it, my friends. Anyway, the bottom line is that it's actually quite easy to fall through the event horizon, both physically and mathematically. Of course, once you're inside the event horizon, we still have that central singularity to contend with. Unfortunately, that one can't be eliminated by a simple change in coordinates. But can that point of infinite density truly exist? Actually, Einstein's theory and the Schwarzschild solution derived from it suggest it must exist. The apparent inevitability of this singularity might be evidence that general relativity itself is incomplete. But to better grasp why the central infinity is unavoidable in Einstein's theory, we have to revisit that coordinate shift at the event horizon. There, the causal roles of space and time effectively switch places, and the central singularity becomes not so much a specific location in space, but rather an unavoidable future. To truly comprehend this, we're going to need an entirely separate discussion. Get ready to explore what happens when the causal roles of time and space are fundamentally swapped within spacetime. The special theory of relativity tells us that one person's past might be another's future. When time itself is relative, this naturally raises the threat of paradoxes. Tonight, we'll peer even deeper into Einstein's theory to discover that the unbreakable ordering of cause and effect emerges when we uncover the causal geography woven into the fabric of spacetime. Recently, we've been discussing the strange nature of spacetime in the immediate vicinity of a black hole's event horizon. Very soon, we'll actually be dropping below that horizon to examine the interior of the black hole. Inside, space and time effectively swap their fundamental roles. But to truly understand that bizarre statement, we need to think a bit more about how the flow of time is actually described within relativity. Today, we're going to look at the amazing geometric structure that time, or more precisely, causality, imprints upon the very fabric of spacetime. First, let's quickly recap a few key ideas from Einstein's special theory of relativity. There are two previous episodes, in particular, that will be quite helpful here if you find you need more background. Special relativity tells us that our experience of both distance and time is, well, relative. If I accelerate my rocket ship to half the speed of light, the distance I need to travel to a nearby star dramatically shrinks from my point of view. An observer I leave behind on Earth, equipped with an incredible telescope, would see me traveling the entire original distance, but they would perceive my onboard clock as having slowed down. The combined effects of this length contraction and time dilation allow both the moving and stationary observers to agree on how much everyone has aged by the end of the journey. Everyone agrees on the number of clock ticks that occurred on everyone else's clock. They just don't agree on the total duration of all those ticks as measured by their own stationary clocks. Remember, time measured by a moving observer on their own clock is called proper time. But simply counting those clock ticks isn't the most effective way for everyone to agree on spacetime relationships. There's this concept called the spacetime interval that connects observer-dependent perspectives on the length and duration of any journey. All observers will always agree on this interval, even if they disagree on the delta x distance and delta t7's time of that journey. We've discussed it before, but it's a challenging concept to intuitively grasp. However, we want that intuition because, even more than proper time, the spacetime interval actually defines the flow of causality. In relativity, three-dimensional space and one-dimensional time merge into a single four-dimensional entity called spacetime. To keep our sanity, We typically represent this on a spacetime diagram, plotting time on one axis and only one dimension of space on the other. In this simplified picture, we'll clearly see our causal geometry emerge. Even in this simplified representation, there's no such thing as truly standing still on a spacetime diagram. If I don't move through space, I'm still traveling forward in time at a speed of exactly 1 second per second, according to my own proper time clock. Motion at a constant velocity appears as a sloped line on this diagram, and the time axis is scaled so that the speed of light is always represented by a 45-degree line. Now, let's imagine we have a group of spacetime travelers. They all start at the origin, where both x and are 0. They race away tonight. We're going to dive into the truly wild world of black holes. These aren't just the weirdest things out there in the cosmos. They actually offer us the sharpest tests for understanding how reality itself functions. They come into being when a huge amount of mass gets squished down past a certain crucial point. But their importance goes way beyond just how they're made. Black holes are like the ultimate extreme labs in the universe. They force general relativity and quantum mechanics to clash head-on. In this extended journey, we're taking a look back through years of discoveries to spend some time exploring how these incredible objects form, how they change over time, and ultimately, how they help us put our deepest ideas about reality to the test, and maybe even bring them together. So, before you get comfortable, take a moment to like the video and subscribe. Let me know in the comments where you are in the world and what time it is for you. Black holes stand out as some of the most peculiar entities we know of in the entire universe. To even begin to imagine making one, we need to bring together both general relativity and quantum mechanics. We'll explore exactly how that happens. Previously, we've discussed what black holes truly are. We've talked about them as structures described by general relativity, as specific areas of spacetime where the boundary's curvature essentially cuts off the inside from anything we can observe in our universe. Now, it's a good idea to watch that earlier discussion if you haven't already. These are some pretty abstract concepts, and to the left and the right for 5 seconds, according to their own personal watches. They're all moving at different velocities, some getting very close to light speed, but none ever actually exceeding it. The path each one carves out through spacetime is known as their world line. My own world line, if I stay still in space, only extends forward through time, and the little tick marks on the time axis directly correspond to the ticks on my own proper time clock. The faster a traveler moves through space, the longer their world line appears to be on this diagram. This isn't just because of their speed, though. To me, observing them from a stationary position, their clocks seem to tick slower. They measure their journey using these slowed-down clocks. So, I see them traveling for a longer apparent duration. When we account for this, we find that our spacetime travelers end up arranged along a curved shape that looks like this. This specific shape is called a hyperbola. If we draw a connecting line at each traveler's identical proper time tick, we get a series of nested hyperbolas. But these aren't just a pretty pattern. These curves are like the contour lines that define the slope of causality down which time itself flows. They're etched into the very fabric of spacetime by the equations of special relativity. But to truly understand why this is, we need to see how these proper time contours appear from the perspective of other spacetime travelers. Instead of using complex equations, we can visualize this with geometry. First, we need to redraw the spacetime diagram from the point of view of one of our other travelers. To transform the diagram, we need to figure out what they perceive as their own space and time axis. Their time axis is straightforward. They see themselves as stationary, So their time axis is simply their own constant velocity world line. And what about their x-axis? Well, from my stationary viewpoint, I define my x-axis as a long string of space-time events at different distances, but all happening at exactly the same moment, at time t-geo. To observe those points, I simply wait until the light from them has had enough time to reach me. At every future tick of my clock, a signal arrives from the left and the right, and I use that to build up a set of simultaneous events that define my t-x axis. Our traveler does the same thing, but from my perspective, their clock is running slow, so I see them registering signals at a different rate. At the same time, they're moving away from signals originating on the left and towards those coming from the right, which affects which signals they perceive as simultaneous at any given instant. The traveler then concludes a set of simultaneous events that, to me, are not simultaneous at all. But here's the key: there's no single, preferred reference frame. Their sloped x-axis is perfectly correct for them. Even just by doing this graphically, we can see that the traveler's x-axis is rotated by the same angle as their time axis. That happens because we insist that everyone, no matter their motion, observes the speed of light to be the same, always a 45-degree line on the space-time diagram. Moving between these different reference frames is now simply a matter of straightening up our traveler's axis. In essence, we grid up the diagram with a set of lines running parallel to these new axes, and then we square up everything while keeping our intersection points fixed. My original world line now appears to be speeding off to the left, while our traveler remains motionless. We've just performed what's called a Lorentz transformation, but using visual geometry rather than mathematical formulas. This transformation allows you to calculate how properties like distance, time, velocity, and even mass and energy shift between different reference frames. But watch what happens if I attach little pens to all of those intersection points on the grid. When I transform between frames, those pens trace out our hyperbolas. Those intersections represent specific locations of space-time events relative to the origin. They will always land on the same hyperbola, no matter which observer's reference frame you choose. I mentioned that these contours show where clocks, moving from the origin, reach the same count of proper time. But more generally, each contour represents a single, specific value for the space-time interval. The delta x and delta t of an event at the end of a traveler's world line might change depending on who is observing, but the hyperbolic contour they land on, the space-time interval, will not. This is because the space-time interval itself comes directly from the Lorentz transformation as the only measurement of space-time separation that remains unchanged, or invariant, under that transformation. Now we can finally get to why this concept is so important and what it truly signifies. It might seem counterintuitive that an event very close to the starting point in both space and time can be separated from that origin by the same space-time interval as an event that is very far away in both space and time. The hyperbolic shape of these contours seems to demand this. But remember, it takes the same amount of proper time to travel from the origin to a nearby, near future event compared to a distant, far future event, as long as both are on the same contour. From the perspective of a particle carrying some causal influence, those points are equivalent. The space-time interval tracks this fundamental causal proximity. We can think of these lines as contours on a kind of causal landscape. The way I've defined the space-time interval, it becomes progressively more negative as we move forward in time. So, we can imagine this as a valley dropping away from us here at the origin. I naturally slide through time by following the steepest path, straight down. I can alter that path by expending energy to change my velocity. However, doing so simply realigns the contours, so I always find myself sliding down the steepest available path. There's no point anywhere, downhill, that I cannot eventually reach, provided I can get close enough to the speed of light. In fact, the closest downhill contour defines the forward light cone for anyone, anywhere on the spacetime diagram. But going, Phil, is impossible as long as the cosmic speed limit, the speed of light, is maintained. Breaking that speed limit and sliding uphill are essentially the same thing. To reverse the direction of your changing spacetime interval is to fundamentally reverse the direction of causality. It's like trying to travel backward in time. The spacetime diagram we've been looking at today describes a flat, or Minkowskian, space where traveling faster than light is the only way to flip your spacetime interval. But in the incredibly curved space found within a black hole, that interval actually gets flipped for you. We'll soon see how this strict requirement of a forward causal evolution leads to some truly remarkable predictions when we attempt to calculate the spacetime interval for regions below the event horizon. Tonight on Spacetime, we're going to talk about time-space, which refers to the strange reversal in the roles of space and time that occurs mathematically when we descend below the event horizon of a black hole. What does this bizarre statement, space and time switching roles, even truly mean? Is this spacetime dyslexia purely a quirk of the mathematics, or does it correspond to genuinely mind-bending reality? We've been building up to this particular topic, so you might want to pause right here and revisit these earlier episodes if you feel you need a bit more background. Okay, let's get started. First, we'll consider what the flow of time looks like without any black holes or even any curvature in space-time. When we explored the geometry of causality, we observed that a quantity we called the spacetime interval dictates the flow of cause and effect. This interval represents the only reliable ordering of events in a universe where everything else is relative. I'm going to show you the mathematical expression one last time, and then we'll return to visualizing all of this graphically. The spacetime interval is defined like this for our familiar, flat, or Minkowskian space. Different observers might report that two events are separated by different distances, delta x, and by different amounts of time, delta t. However, all observers will consistently record the same spacetime interval. If one event directly causes a second event, the spacetime interval between them must be zero or negative. This simply means that a causal link, potentially traveling at the speed of light, could have connected them. You could say that an object at a given instant in spacetime is caused by whatever version of itself existed an instant earlier. So, the world lines of objects naturally have decreasing spacetime intervals as they progress. In fact, for a normal forward temporal evolution to occur, a negative spacetime interval is required. In flat spacetime, that negative sign placed in front of the delta t term is what drives this forward evolution. This makes the time-like coordinate, while x is the space-like coordinate. For causality to be maintained, the time-like coordinate must always increase. Reversing causality means flipping the sign of the spacetime interval. In our episode on superluminal time travel, we saw that in flat space, this would imply traveling faster than light, which is, of course, impossible. But if we introduce a black hole, we now have a second way to flip the sign of the spacetime interval. We're about to see how this changes the behavior of time in profoundly strange ways. If we add a non-rotating, uncharged black hole, the spacetime interval equation transforms into this. This specific form comes from Carl Schwarzschild's solution to Einstein's field equations, which was the very first accurate mathematical description of a black hole. I've left out a few terms for simplicity. This equation assumes no orbital motion, only movement directly towards or away from the center of the black hole, which is located at a distance r away. That RS term represents the Schwarzschild radius, which is the radius of the event horizon. Very far away from the event horizon, the Schwarzschild interval simplifies and essentially becomes the familiar Minkowskian interval, and time and space behave themselves, remaining nicely separated. But if an object gets very close to the event horizon, so is just a little bit larger than RS, those terms in the two brackets describe an extreme warping of spacetime. However, as long as you remain outside the event horizon, time mostly behaves as expected. A negative spacetime interval still indicates causal movement forward, and the only way to break causality is still by traveling faster than light. Things change radically once you're below the event horizon. When R becomes smaller than RS, then both of those bracketed terms become negative. The entire delta R squared term is now negative, and the delta T squared term is positive. Below the event horizon, there is only one way to maintain the respectable causal progression expected of any well-behaved temporal entity. That is to fall inward, to have a non-zero delta R term. As it happens, you don't actually have a choice in the matter. Space itself is falling inward, faster than the speed of light, directly towards the central singularity. It carries you along with it, and, as it does so, it drives your personal clock forward. In the mathematics, the coordinate, or, which once represented a distance, now provides the negative sign needed to maintain your causal flow. It effectively becomes time-like. It becomes unidirectional. Meanwhile, the coordinate previously known as, or time, has lost its negative sign and become space-like. So, it can now be traversed in any direction, or not traversed at all. But what does all this, time-space switching, actually look like? Let's fall into the black hole one more time, now visualizing it graphically instead of just mathematically. Back out here in the regular universe, it's pretty obvious where the past ends and the future begins. On our ever-popular spacetime diagram, we see a sharp division between the two. Our past light cone encompasses all of spacetime that could possibly have influenced us, while our future light cone shows us all the parts of the universe that we might ever hope to encounter or influence. Which direction is the future? It's ahead along our time axis and at right angles to all of our space axes. Our future light cone points fixedly forward, encompassing all spatial directions equally. This is no longer true if we introduce gravity. Close to a massive object, your future is no longer at right angles to space. It becomes slightly tilted in the direction of that mass. If you send out a burst of future, defining light rays, they won't spread out evenly, because they're being bent towards the gravitational field. As you approach the event horizon of a black hole, more and more of these light rays are turned inward, towards the event horizon. Your future light cone and your time axis begin to merge with the inward radial axis of the black hole. At this point, it's time we switch to a different kind of diagram. Close to and within the black hole, the Penrose diagram is much more useful. It deals with the extreme stretching of space and time by compactifying lines of constant space or time near its boundaries. We've talked about these diagrams before, but an important thing to remember is that the lines of constant space and time are curved on a Penrose diagram so that light cones always remain upright, and light always travels at a 45-degree angle, even inside the black hole. This entire diagonal line on the diagram represents the event horizon. Watch what happens to our view of the universe as we get closer to it. Our entire future light cone begins to encompass more and more of the event horizon. That last tiny sliver remaining is a narrowing window directly above you, representing the possibility of escaping at a speed very close to light. Meanwhile, our past light cone now encompasses light that has been struggling to escape from just above the event horizon since the distant past, but we still see nothing from below the horizon. Yet, As soon as we actually pass the horizon, everything changes dramatically. The outside universe exits our future light cone, which now points solely towards the singularity. We also start to encounter a whole new set of photons from the past. At the exact moment of crossing, light rays from the event horizon itself suddenly become visible. In fact, we plummet through what feels like a sea of light that is eternally climbing outwards but making no real progress. After that, we gain access to the history of the black hole's interior. As we fall, carried by the faster, then light flow of spacetime, we overtake light that is pointing outwards. This light isn't actually making any headway outwards. It's trying to swim upstream, unsuccessfully, against the faster, then light cascade of spacetime. Some of this light might even be from the collapsing surface of the star that originally formed the black hole, emitted long before we even entered the event horizon. It appears to come from below us because it's attempting to climb upwards. In reality, though, it was emitted at larger radii than wherever we encounter it. Also, within our past light cone are light rays that are pointed inwards, some of them coming from the outside universe. This light actually overtakes us as we fall. This is light that entered the event horizons after we did and appears to reach us from above. We can try to move towards either source of light, down towards light from the black hole's past, or up towards light from the black hole's future. Those directions, those spatial freedoms, are now described by what was once the time coordinate, but it's no longer time-like. You can traverse it in either direction, making it space-like. Doing so isn't actually traveling in time, even though there's a sense of past events in one direction, the collapsing star, and future events in the other. Everything that fell into the black hole after us. But remember that our future light cone actually just points directly towards the singularity. If we try to accelerate in either direction, up or down, we just quicken our demise. It's best just to fall. It's the last mercy granted by the black hole. It transports us to our doom by the slowest possible path, unless we resist. Below the event horizon, there's still a sense of spatial openness and downness. However, the old radial dimension isn't space-like anymore. It's become time-like. Every photon that reaches us was emitted at some larger radius than wherever we encounter it. Even if it's ancient light struggling outwards, the past is radially outwards, and all possible future directions lead radially inwards, in the same way that all world lines move towards the future in the outside universe. Time is layered radially, and is time-like, unidirectional. The singularity becomes a future time, not a central place. In fact, the Schwarzschild metric actually provides two separate spacetime maps within a single equation, one for above and one for below the event horizon. The coordinates r and t play fundamentally different roles in those distinct regions. There are other coordinate systems where that switch never appears to happen. But this mysterious dimensional flip does offer us some fascinating insight into how time and space blend together in what is perhaps the strangest place in all of spacetime. Lurking deep within the mathematics of Einstein's general relativity is an object even stranger than the enigmatic black hole itself. In fact, it's like the black hole's mirror twin, the white hole. Some even speculate that these might be the very origin points of our universe. The astrophysical phenomenon of the black hole has captivated the imaginations of scientists and science enthusiasts alike for many, many decades. When the idea first emerged from Einstein's general theory of relativity, physicists wondered how seriously they should take this purely mathematical description of an inescapable region of spacetime. Astronomers have since conclusively shown that black holes are very real, with compelling evidence that quasars, X-ray binaries, and even the very center of our own Milky Way galaxy all harbor these gravitational behemoths. But the same mathematical framework that predicts the existence of the black hole also describes entities that are even more bizarre, but whose connection to reality is still unclear. One such entity is the white hole. A white hole is, in a very literal mathematical sense, the exact opposite of a black hole. In essence, it's a time-reversed black hole. A black hole is defined as a region of spacetime where everything flows inward, with a one-way boundary called the event horizon, from inside of which nothing can ever escape. That makes a white hole a region of spacetime where everything flows outward. It also possesses an event horizon, but that horizon acts as a barrier to entry, not to exit. Nothing from outside a white hole can ever enter it, and everything inside must inevitably be ejected. Not even light can leave a black hole, which explains the black part. But light can only leave a white hole. So these objects would be expected to radiate intensely, and white would be an understatement. Now, before everyone gets too excited, white holes are most likely a product of mathematical imagination. But they are a truly fascinating concept, and the idea might actually help us understand the very beginning of the universe. White holes first appeared in the earliest mathematical descriptions of black holes. Just a few months after Einstein published his general theory of relativity, Carl Schwarzschild found a solution to its equations for a very specific case, a single point of mass in an otherwise empty spacetime. The resulting Schwarzschild metric actually describes a black hole, the simplest possible kind of black hole, one without spin, without electric charge, and without change. An eternal black hole that doesn't grow or shrink and has always existed. We've talked quite a bit about the bizarre behavior of space, and especially time, at and below the event horizon of a black hole. Here's a little playlist if you want a refresher. But here's the quick summary. The time that passes inside a black hole is not part of the past or future history of the outside universe. From the perspective of an outside observer, any events happening at the event horizon, including something falling into it, appear to occur infinitely far in the future. Once you actually fall into a black hole, the Schwarzschild metric tells us that space and time switch their fundamental roles. The singularity no longer occupies a central location in space. Instead, it now represents an inevitable future time. Now, a real black hole forms from the gravitational collapse of a massive star's core. After that collapse, the future singularity comes into being. And in the past, well, there's just a star. But what does this idealized eternal black hole look like if we trace its history backward in time? If we follow the Schwarzschild metric back in time, we uncover something very strange. We find the singularity again, this time lurking infinitely far in the past. From the viewpoint of the outside universe, the singularity of an eternal black hole exists both in the infinite future and in the infinite past. That might sound strange, but it gets even stranger. To truly grasp what this eternal black hole looks like, we're going to need to use a tool we've already played with, the Penrose diagram. To refresh your memory, in a Penrose diagram, the x and y axes are redefined from simple space and time coordinates to new coordinates that merge space and time. They effectively compactify space-time, meaning that time gets compressed towards the edges of the diagram, and these borders correspond to the infinite past and infinite future. Also, lines of constant distance and time are curved on these diagrams so that light paths always travel along 45-degree angles, even inside the black hole. We are currently observing from here and now, at the very center of the diagram. If we place an eternal black hole far to the left, then the future left boundary of the diagram represents the black hole's event horizon. Any movement towards the left brings you closer to that event horizon. The event horizon itself is represented by a 45-degree line. In our unusual Penrose coordinates, this line signifies a constant distance from the center of the black hole. Light traveling along that 45-degree angle takes an infinite amount of time to escape the event horizon. And the region beyond that line represents the interior of the black hole. There, the dimensions of space and time actually switch roles. The once vertical contours of space are now time-like and flow relentlessly towards the future singularity. These two regions, our universe and the black hole interior, are simply the Schwarzschild metric mapped out using these specialized Penrose coordinates. But our map isn't yet complete. Remember, this is an eternal black hole, so it must also exist in the past. If we map into the past, we observe a time-reflected version of our future black hole. Everything about it is time, reversed. The singularity is now a past event. Space within this region is time-like, but instead of flowing towards the singularity, it flows away from it. And the event horizon is now a barrier to entry, not to exit. We can make some sense of the behavior of this strange region by using the Penrose diagram. Imagine that something in our past was traveling at the speed of light and trying to reach the past event horizon. There's no way it could get there unless it traveled faster than light. Oh, it would reach an event horizon, but only the event horizon of our future, where it would plunge into a regular old black hole. Remember that all of this description is from our perspective, far away from the event horizon. We can never actually see anything cross the horizon. The light rays from any such crossing reach us infinitely far in our future, even if the black hole plunge began far in the past. So, the past region of the eternal black hole has an event horizon that acts as a barrier to entry. But also, light rays within that region must move up on the diagram, which suggests they must exit into the outside universe. Anything inside this past eternal black hole must be ejected. So far, this region perfectly matches the description of a white hole. The eternal black hole of the past technically is a white hole. However, it's not one that we could ever observe for two main reasons. First, light rays exiting that past white hole can never actually reach us. The past singularity and past event horizon are infinitely far in the past from our point of view. Light would have to traverse infinite time to reach our current location. And second, there's no such thing as an eternal black hole. The universe hasn't existed for eternity, and it certainly didn't begin with black holes already in place. Even though this type of white hole isn't observable in practice, some physicists have taken the mathematical description very seriously. The math describing the white hole is a perfectly valid application of the Schwarzschild geometry. It completely obeys general relativity. It really is just a black hole, but viewed backward in time. Yet, general relativity is time reversal symmetric. Something that can happen forward in time should, in principle, also be able to happen in reverse. So, could new white holes actually form in our universe? Well, theoretically, yes. But to create one, you would need to reverse entropy. You see, although it's mathematically possible to construct a white hole within general relativity, there are other fundamental laws of physics that the universe must obey. For example, the second law of thermodynamics. It demands that entropy, which is a measure of disorder or randomness, must always increase. This law effectively defines the direction of time's flow. To reverse time, you would need to break this law. You would need to decrease entropy. Now, this is technically possible because entropy is a statistical phenomenon. Very rare, localized reductions in entropy do happen. As long as, globally, entropy increases on average, it's conceivable that an incredibly rare, profound dip in entropy could lead to an effective reversal of time, and a white hole could briefly form. However, it would immediately explode in a burst of energy as soon as entropy and time resumed their normal flow upwards and forwards. We actually discussed a case where a random drop in entropy led to something very much like a white hole in a previous episode. It's even been speculated that the Big Bang itself originated from such a profoundly improbable entropy dip. And as it happens, the Big Bang looks, at least mathematically, very much like a white hole. It's an expanding outpouring of space-time containing an enormous amount of energy. And the bang itself can never be entered. After all, it's in the past. The primary difference between the Big Bang and a white hole is that the former possesses no singularity. It happened everywhere at the same time. Still, that hasn't stopped physicists from having fun with the idea. It's been proposed that when a black hole forms, a white hole simultaneously forms on the opposite side. Energy entering the black hole then exits the white hole. Physicist Lee Smolin takes this idea a step further, suggesting that the resulting white hole is actually the Big Bang of a new, baby universe, and that, in fact, our own universe formed in precisely that way. More on that another time. But speaking of other universes, it turns out that we haven't quite finished building our Penrose diagram yet. The past white hole was revealed when we traced the eternal black hole backward in time. In essence, what we did was to maximally extend space-time. We required that all paths be traceable through infinite past and future space, provided they don't hit a singularity. But what about light rays entering or leaving our eternal black hole from the era's opposite side? The mathematics of the Schwarzschild metric describes an entirely independent region of spacetime, existing parallel to our own. It looks like an identical, alternate universe on the other side of the black hole, accessible through what we call an Einstein-Rosen bridge, which is better known as a wormhole. In the not-too-distant future, we'll investigate the actual reality of this mysterious parallel patch of spacetime. He was perhaps the greatest genius of our era. Stephen Hawking peered behind the curtain of reality and caught a glimpse of the universe's true inner workings. He inspired all of us to pursue our curiosity, no matter the challenges. However, his most significant legacy is his actual work. He made profound contributions across many fields of physics, from quantum theory to cosmology. Our tribute tonight is to bring you Stephen Hawking's most famous discovery. I'm Matt O'Dowd. This is Spacetime, and it's time for Hawking radiation. Soon after Einstein revealed his groundbreaking general theory of relativity in 1915, physicists quickly realized that it allowed for the possibility of catastrophic gravitational collapse in places of extreme density, such as the dead core of a massive star. Space and time could be dragged inward to create a literal hole in the universe, a boundary in spacetime called an event horizon, which could be entered, but from beyond which nothing could ever return. Once formed, there was nothing, in theory or imagination, that could bring any consumed material back to the outside universe. These black holes, it was thought, should exist forever, only growing larger, never shrinking, or so we believed until 1974, when a young physicist named Stephen Hawking published a paper in Nature titled Black Hole Explosions. In this paper, and in a follow-up publication in 1975, he attempted a novel unification of quantum mechanics and general relativity to demonstrate that black holes shouldn't be so black after all. They should, in fact, leak. They should emit what we now know as Hawking radiation. There's a very popular, simplified description of how Hawking radiation supposedly works. It goes something like this. Empty space constantly buzzes with activity as pairs of virtual particles, matter and antimatter, spontaneously appear and then immediately annihilate each other, briefly borrowing energy from the vacuum itself. But when this happens very close to a black hole, sometimes one particle from the pair will be swallowed by the event horizon, leaving the other free to escape and taking its stolen energy with it. That energy can't come from nothing, and so the black hole itself pays the debt by slowly leaking away its own mass. This is a nice, easily digestible picture. But how accurate is it? In fact, if we follow the narrative of Hawking's original calculation, the story sounds quite different. We've come a long way over the past few months, building up the necessary knowledge. We'll need to follow that intricate calculation. Watching some of those previous episodes, either now or after this video, will be quite helpful. But if you feel you're ready, let's take a deep dive into the quantum field theory of curved spacetime to glimpse the true nature of Hawking radiation. Actually, a quick refresher on quantum field theory can't hurt. Space is not truly empty, it's filled with quantum fields. These fields can oscillate with different frequencies, much like the many possible vibrational modes on a guitar string. A particle, in this analogy, is like a specific note played on that string. And just like a real guitar note, actual particles tend to be made up of many different vibrational modes. Those underlying vibrational modes are still present even when there are no real particles. They constantly fluctuate in energy due to quantum uncertainty. And those fluctuations are what give us what we think of as virtual particles. Now, don't take the existence of virtual particles too literally. They're primarily a mathematical tool for calculating the infinite ways in which a fluctuating quantum field can behave. One way that quantum fields are very different from guitar strings is that they can possess both positive and negative frequencies. A negative frequency can be thought of as a mode that effectively travels backward in time, and it can be interpreted as corresponding to antimatter. Now, that's a whole new level of weirdness all on its own, and we've discussed it in another video. When a quantum field is in a vacuum state, there's a delicate balance between its positive and negative frequency modes. You can crudely think of this as a balance between virtual matter and antimatter particles. These all virtually annihilate or cancel each other out so that no real particles actually exist. This is perfectly fine in flat space, but spatial curvature can severely disrupt the balance of these underlying quantum field modes by introducing horizons. Horizons effectively cut off access to certain modes of the quantum fields, disturbing the equilibrium that defines the vacuum state. Stephen Hawking understood that black holes, with their incredibly extreme spacetime curvature, would wreak havoc on quantum fields in their vicinity. But what exactly would the effect be? To answer that question properly, he would have needed a complete unification of general relativity and quantum mechanics, a theory of quantum gravity, a theory of everything. That theory didn't exist then, and it still doesn't exist yet. Not to be deterred by the seemingly impossible, Hawking devised an ingenious workaround. The narrative of Hawking's mathematics goes something like this. He imagined a single path through spacetime, a trajectory traveling at the speed of light, called a null geodesic. This path extends from the very distant past to the very distant future. This is a perilous path. It passes right through the location where a black hole is about to form in the instant before it actually forms. In fact, it is the very last trajectory that manages to do so. It emerges barely ahead of the forming event horizon. Hawking imagined a simple quantum field tracing this path. A field that is initially in a perfect vacuum state before the black hole's formation. But he discovered that this extremely close shave with the black hole profoundly disturbs the fundamental vibrational modes that define the fluctuations of the vacuum. By the time this trajectory has found its way back out into flat space again, those fluctuations look like real particles. A distant observer in the far future sees radiation appearing to come from the black hole. Hawking's imaginary path, stretching from the distant past to the distant future, was a stroke of genius. It allowed him to compare the state of the vacuum in two distinct regions of flat space, far away from the black hole. These are regions where the nature of vacuums, quantum fields, and particles are perfectly well understood. But to understand the effect of the close encounter with the black hole, he needed an uneasy marriage between quantum mechanics and general relativity. In the absence of a complete theory of quantum gravity, Hawking needed a hack. That hack was the Bogoliubov transformations. Try saying that 3 times fast. These transformations can be used to approximate the effect of curved spacetime on quantum fields by smoothly connecting regions of flat space. They describe a kind of mixing of the positive and negative frequency vibrational modes, a mixing that is caused by that curved space. The physical interpretation of this mixing, achieved via the Bogoliubov transformations, is quite tricky. In fact, there isn't just one single, universally agreed upon valid interpretation. Hawking's calculation talks about scattering. Certain modes of the quantum field are scattered, or deflected, by the intense gravitational field of the forming black hole. They are subtly nudged off their narrow escape path and, as a result, are lost behind the forming event horizon. Meanwhile, other modes manage to avoid this scattering and continue on unscathed. With the permanent loss of certain fundamental modes, the vacuum state must then be constructed from the remaining modes. That distorted vacuum then appears to be filled with particles. The nature of these lost modes tells us what Hawking radiation should actually look like. Black holes tend to scatter modes with wavelengths that are similar to their own physical sizes. The quantum field that emerges is distorted within that same wavelength range. And so, it produces wave packets. It creates particles that also have wavelengths roughly as large as the event horizon itself. So, the more massive the black hole, the longer the wavelength of the radiation it emits. Hawking calculated the frequency distribution of this radiation and uncovered something truly incredible. It should look exactly like thermal radiation. Black holes should have a faint heat glow with an apparent temperature that depends directly on their mass. More precisely, this temperature is inversely proportional to the surface area of the event horizon. Large black holes should appear very cold, radiating excruciatingly slowly, but small black holes should appear hot, and the smallest ones should radiate explosively. Okay, so what about that popular picture of particle-antiparticle pairs being pulled apart by the event horizon? Well, Hawking's math describes a splitting or mixing of these pure positive and negative frequency modes. It's a fair interpretation to see this mixing as the promotion of what were once virtual particles into actual reality. And for the modes that manage to escape, there exists a corresponding set of modes, intricately linked by quantum entanglement, that are trapped behind the event horizon. We can interpret those trapped modes as corresponding to the swallowed antiparticle partner. So, the idea of split matter-antimatter pairs in the popular explanation is a reasonable approximation. However, there are good reasons to be cautious about certain aspects of this simplified picture. Firstly, this radiation isn't localized to a specific point. Remember, Hawking radiation has wavelengths the size of the event horizon, meaning the size of the entire black hole itself. These are the de Broglie wavelengths of the created particles, and they tell us that there's an enormous quantum uncertainty in the precise location of these particles. Hawking radiation must appear to originate from the black hole globally, not from specific points on the event horizon. In fact, an observer in freefall, smoothly passing through the horizon, wouldn't actually see anything unusual. To them, space is locally flat, and the vacuum should still look like a vacuum. This radiation is only truly visible to distant observers. Well, there is one interesting exception. If you were to fire up your jetpack and hover at a fixed distance just above the horizon, then you would actually see particles. You would observe something called Unruh radiation. We'll explore its fascinating relationship to Hawking radiation in a future discussion. By the way, Hawking radiation is primarily composed of photons and other massless particles. To produce particles with mass, the energy of the radiation would need to be high enough to account for the rest mass of that particle. So, it's generally okay to interpret the narrative of Hawking's calculation as the splitting of entangled matter and antimatter pairs, even if it's really just a heuristic interpretation. It's the exact cause of the splitting that remains hard to pinpoint definitively. We can think about positive and negative frequency modes being mixed due to scattering, perhaps by the as yet undiscovered graviton, the hypothetical quantum particle of gravity. Other physicists have derived Hawking's result using very different, seeming narratives. For example, in 2001, Parikh and Wilczek arrived at the same thermal spectrum for Hawking radiation by considering particles escaping from stars beneath the event horizon through a process called quantum tunneling. The common thread uniting all these approaches is quantum uncertainty. For example, uncertainty in position and momentum can lead to particle pairs that were once in the same location, or modes that were once on the same world line, becoming separated by the event horizon. Alternatively, uncertainty in energy can directly lead to particle creation. Whichever way you choose to interpret it, it's incredibly difficult to avoid the conclusion that black holes do indeed emit particles. The fact that different derivations lead to exactly the same result, or that the radiation consistently appears thermal, can't possibly be a coincidence. It's very hard to make Hawking radiation simply disappear from the mathematics. And believe me, Stephen Hawking himself tried to find ways around it. Ultimately, however, all these calculations, while utterly brilliant, are still essentially hacks. Without a complete quantum theory of gravity, the precise origin of Hawking radiation will remain somewhat mysterious, and there are other profound mysteries we haven't even touched upon yet. For example, what actually happens to the particles or modes that are trapped by the black hole? How do they end up reducing the black hole's mass instead of increasing it? And then there's the famous information paradox, in which Hawking radiation appears to destroy what should be a conserved quantity, quantum information. We'll tackle all of these intricate questions in future episodes. For now, we must conclude that black holes radiate, and in doing so, they slowly evaporate. The scariest monsters of general relativity are ultimately unraveled by the brilliant mind of Stephen Hawking and a mysterious quirk of quantum spacetime. Black holes seem like they should possess no entropy at all, but in reality, they hold most of the entropy in the entire universe. Let's try to understand why this is. At first, it seemed that black holes were so incredibly simple that they should have zero entropy. Well, it turns out they contain the vast majority of the universe's total entropy. Let's explore why. Because this profound fact might actually force us to conclude that the universe itself is a hologram. Black holes pose a significant problem for our understanding of physics. They are the inevitable outcome of extreme gravitational collapse, at least according to the equations of Einstein's general theory of relativity. That theory is one of the most thoroughly tested and confirmed in all of physics, which means we should probably trust in the existence of black holes. Furthermore, we've directly observed them through their powerful gravitational effects on surrounding space, and through the gravitational waves produced when they merge. And yet, if black holes truly exist, which they apparently do, they appear to contradict other fundamental theories in physics that are just as sacred as general relativity. They create all sorts of issues with quantum theory, which we've discussed before and will briefly review in a moment. But they also present an apparent conflict with the very notion of entropy and the second law of thermodynamics. It was while deeply pondering that specific conflict that Jacob Bekenstein realized an incredible connection between black holes and thermodynamics. His profound insight launched an entirely new way of thinking about the universe in terms of information theory, and ultimately led to the holographic principle, which I promise we're getting to and are almost there. But first, you are going to need to know more about why black holes contain most of the universe's entropy. Okay, I'm getting way ahead of myself. Let's actually rewind back to those episodes where we first laid out the black hole information paradox, because those discussions are going to be absolutely critical to a proper understanding here. We're also rewinding to the late 1960s and early 1970s, when physicists made a very odd realization about black holes. What they understood is that it simply doesn't matter what kind of material falls into one. From the perspective of the outside universe, black holes can only ever possess three fundamental properties: mass, spin, and electric charge. This is famously known as the no-hair theorem, and it strongly suggests that most of the detailed information about anything that falls into a black hole is permanently lost to the outside universe. But a fundamental tenet of quantum mechanics is that quantum information can never be truly destroyed. So, if black holes eventually evaporate, as Hawking discovered and as we've also covered, this evaporation process should destroy a black hole's internal quantum information, giving us the infamous black hole information paradox. Eventually, a possible resolution to this paradox was proposed by Gerard Hooft. He described a mechanism by which the information contained by infalling particles could potentially be preserved on the event horizon of the black hole itself. From there, this information could then be imprinted onto the outgoing Hawking radiation, allowing the information to escape back into the universe. Okay, problem solved, right? But in our previous discussions, we skipped over the key insight that actually started all of this. It all began with Jacob Bekenstein thinking deeply about black hole entropy. Okay, first, entropy. Yes, we've talked about that quite a lot recently. Also, it's almost as if all of those episodes are starting to connect and come together. Almost like we planned this. Go and watch that background material if you're feeling behind. But of course, for now, I'll give you a quick summary of entropy. So, we can think of entropy in two main ways. One, it's a measure of how evenly energy is spread out within a system. High entropy typically means thermal equilibrium, where energy is very uniformly distributed and therefore cannot be easily extracted in a useful way. And two, entropy also measures the amount of unknown information that you would need to perfectly describe the system's internal state. Things like all the individual particle positions, their velocities, and so on. The higher the entropy, the more randomly distributed its particles are, and the more possible microscopic configurations could lead to the same macroscopic state. The higher the entropy, the less you can guess about the properties of individual particles based solely on the system's global properties, such as temperature, volume, or pressure. Okay, so the second law of thermodynamics states that the entropy of an isolated system must always either increase or stay constant. This means energy naturally tends to spread out evenly, and particles tend to randomize their arrangements, which reduces our specific information about their microscopic states. How does this fundamental law relate to black holes? Let's imagine making a black hole and see what happens to entropy. We start, as usual, by collapsing the core of a dead star. Now, that's a high entropy beast, super hot and filled with randomly moving particles. We have almost no detailed information about the individual particles within it, but that information still exists within the universe. The particles, in a sense, know where they are. At the exact instant the star collapses far enough to form an event horizon, it suddenly becomes a black hole. We transition from knowing next to nothing about the object's internal state to knowing, according to the no-hair theorem, everything. We can easily measure its mass, its spin, and its electric charge. And, as per the no-hair theorem, that's all there is to know about it from the outside. The region of space where the black hole formed appears to have gone from a state of very high entropy to zero entropy in an instant, utterly shattering the second law of thermodynamics in the process. Which, to put it mildly, is a major problem. But if you paid close attention to the whole information paradox discussion, you might already be thinking of a potential solution. If quantum information is indeed stored on the surface of the black hole, couldn't we also store entropy there? And then, why not radiate that entropy back into the universe as Hawking radiation? Actually, yes. The resolution to the information paradox also conveniently saves the second law of thermodynamics. That was easy. I thought physics was supposed to be hard. Okay, hang on. Let's think about this a little bit more deeply. It was this apparent violation of the second law that initially prompted Jacob Bekenstein to start thinking about the profound connection between black holes and information in the first place. His groundbreaking insight was this simple observation: the surface area of a black hole's event horizon can never decrease, at least not according to general relativity. So, you know how nothing can escape black holes, ignoring Hawking radiation for a moment. That would imply that black holes can only ever grow larger. They can never shrink in mass or radius. Well, that's not entirely true. If you merge two black holes, some of their combined mass gets converted into energy radiated away in the form of gravitational waves. There's also the Penrose process, which theoretically allows you to extract rotational energy from a spinning black hole. And by you, I mean not you, but rather super advanced, far future civilizations. Gravitational radiation and the Penrose process do reduce black hole mass and radius, or the sum of masses and radii for merging black holes. But there's one property of black holes that no process, other than Hawking radiation, can ever decrease. That is the surface area of the event horizon. Do anything you want to black holes, and their total surface area can only grow or stay constant. Bekenstein saw a striking correspondence between the always increasing event horizon surface area and the always increasing nature of entropy. He also realized that the equation relating the change in a black hole's surface area to the change in its mass closely resembled the original definition of thermodynamic entropy. Change in entropy and internal thermal energy, with change in black hole surface area and black hole mass, respectively. You can also add the work done when you extract energy from the black hole, and it looks just like the equation for the work extracted from a thermodynamic system. Bekenstein had just discovered black hole thermodynamics, but that didn't give him the exact definition for black hole entropy. For that, he turned to Ludwig Boltzmann's foundational definition for entropy. So, entropy can be defined as the amount of information hidden in a system's microscopic configuration, multiplied by the Boltzmann constant. Bekenstein then estimated the amount of information that would be lost into a black hole as it grew larger. Essentially, he conceptually built a black hole out of idealized elementary particles, each containing a single bit of information. And guess what? The information content of a black hole is proportional not to its mass, or its radius, or its volume, but rather it's proportional to its surface area. In fact, the information content is very close to that surface area divided by the number of Planck areas. It's as though each of these minimum possible quanta of area, each tiny patch, contains a single bit of information. Now, just multiply that information content by the Boltzmann constant, and you have the entropy of a black hole, which is directly proportional to the surface area of the event horizon. Bekenstein's connection between surface area and entropy could have been a mere coincidence. At least, it was until Stephen Hawking came along. In 1974, just a year after Bekenstein's first paper on black hole thermodynamics, Hawking published his first paper on Hawking radiation. He showed that black holes radiate random particles, exactly as though they possess a heat glow of a particular temperature that depends on their mass. So, if black holes have a temperature, then they must also have entropy. Good old-fashioned thermodynamic entropy tells us that the change in entropy is equal to the change in internal thermal energy divided by temperature. So, Hawking simply plugged his newly calculated Hawking temperature into that equation, along with the black hole's mass for internal energy, and derived the total entropy contained within a black hole. He arrived at an expression almost identical to Bekenstein's, but with just a slightly different constant of proportionality. So, you get the same result for black hole entropy, whether you figure it out from the amount of information that gets trapped when building a black hole, or the amount of heat that leaks as it evaporates. And crucially, it's proportional to the surface area. How bizarrely consistent is that? I'd say that strongly suggests it's correct. The second law of thermodynamics is saved because black holes do, in fact, possess entropy. In fact, they have enormous entropies, representing the maximum possible for any given volume. So much so that black holes are now believed to contain the vast majority of the entropy in the entire universe. But the true significance of this work wasn't just the solution to some obscure conundrum. It fundamentally changed our thinking about the informational content of the universe itself. Bekenstein's formula was originally derived for black holes, but it also gives the maximum amount of information that can be packed into any given volume of space. In this broader respect, it's known as the Bekenstein bound, and it's proportional to the surface area of that space. This is highly unexpected. Surely, the maximum amount of information you can fit into some patch of space should depend on the Rs volume of that space, as in 1 bit per tiny volume element inside that space. But in reality, the rule states 1 bit per tiny F area element on the surface of that space. That also means that the total information needed to describe any volume of space, regardless of its contents, is proportional to the area bounding that space. I've hinted once or twice that this simple idea directly led to the holographic principle. This is the radical idea that the entire three-dimensional volume of our universe is actually just a projection of information encoded on a two-dimensional surface surrounding the universe. You just need to add a little bit of string theory into the mix. It's a hell of a conceptual leap, considering it all started with Jacob Bekenstein noticing a peculiar similarity between a couple of formulas. It might also be profoundly true, and obviously, we'll be back before too long to talk about string theory and the holographic nature of spacetime itself. These dark, volcanic rocks are a testament to ongoing geological activity, and this particular spot is one of the youngest stretches of land on planet Earth. But the same powerful geological forces that sculpted this land have also provided us with another remarkable window. It allows us to observe a time when the universe was still cooling from the intense fire of its own formation. And to see this, all we need to do is journey to a telescope perched atop the tallest volcano in the world. So, we're currently driving up to the summit of Mauna Kea, on the big island of Hawaii. This is the tallest volcano on the entire planet, reaching an elevation of 200 meters. The oxygen level up here is only about 60% of what you'd find at sea level, but astronomers endure it, because it is widely considered the premier astronomical observing site in the entire northern hemisphere. To native Hawaiians, it is a deeply sacred site, and to astronomers, it's where Earth truly meets the universe. Wow, it's absolutely breathtaking up here. It genuinely feels like being on another planet. I can already distinctly feel the effects of the thinner atmosphere. My natural impulse, bizarrely, is to hold my breath. I must consciously remember to keep breathing. Here we have 13 of the greatest telescopes in the world, operated by 11 different countries. We have the Japanese Subaru telescope, the Twin Keck telescopes. Over here, we see the Canada-France, Hawaii telescope, and this one right here is Gemini. That's where we're headed. We're here to talk about a very special observation. In the spring of 2017, astronomers carefully pointed Gemini's massive mirror towards the constellation of Bootes, often known as the Plowman. They were searching for a faint speck of light that had been initially noticed in one of our vast sky surveys. Astronomers suspected the speck was a quasar, which is a swirling vortex of intensely radiant matter falling into a supermassive black hole. Now, quasars are renowned as the most luminous objects in the entire universe. What was particularly strange about this specific one was its immense distance. Its light was so profoundly redshifted, meaning its wavelength had been stretched out, that astronomers realized that light must have traveled for many billions of years through our continuously expanding universe. This quasar appeared to be more distant than any we had ever observed before. But that doesn't mean we can't unravel its mysteries. And Gemini did exactly that. To discover how, we're going to need to go inside. You simply have to see this. It's truly incredible. Meet the Gemini telescope. This is what a world-class astronomical telescope looks like in this modern era. It is absolutely enormous. I still vividly remember the first time I ever stepped inside a telescope like this. It completely blew me away. Just look at the sheer size of this thing. This is our direct window to the universe. It's quite cold in here. They meticulously keep the dome at the exact temperature of the upcoming night, so that the giant structure of the telescope itself doesn't warp and twist even slightly with the change in temperature. That's a little below freezing right now. And do you hear that sound? That's the cryogenic system at work. They keep the incredibly sensitive infrared cameras at 15 degrees above absolute zero. Let's actually take a moment to talk about light itself. Light is fundamentally a wave, and the wavelength of that wave dictates the specific properties of the light. For example, visible light, the narrow range of wavelengths that our eyes are sensitive to, spans only a tiny fraction of the entire electromagnetic spectrum. That's precisely why we build telescopes, to see beyond what our eyes can. The universe looks dramatically different at various wavelengths. For instance, when viewed in visible light, the Andromeda Galaxy shows us regions where newborn stars are actively forming. Our planet's atmosphere is relatively transparent to visible light, so a ground-based telescope can observe the visible universe just as we can with our eyes. Gemini, however, is specifically engineered to be sensitive to the infrared spectrum. In infrared, the Andromeda Galaxy appears as a beautiful swirl of star-forming clouds and gas. Some infrared light also manages to penetrate our atmosphere, though it certainly helps to be located up here on a mountaintop. Although the air directly above the observatory is incredibly clear, it still causes distant light to blur somewhat. Turbulence in the atmosphere causes incoming wavefronts of light to be warped, which blurs our view of celestial objects. To correct this constant distortion, Gemini employs a sophisticated system called adaptive optics. It features a deformable mirror that actively flexes and bends thousands of times per second to precisely match and correct the warping of incoming light. To achieve this in real time, Gemini actually creates its own artificial guide star by shooting powerful lasers to make sodium atoms at a height of 90 kilometers. Right at the edge of space's smallest should radiate explosively. Okay, so what about the popular picture of particle-antiparticle pairs being ripped apart by the event horizon? Well, Hawking's math describes a splitting or mixing of these pure positive and negative frequency modes. it's a reasonable interpretation to see this mixing as the promotion of what were once virtual particles into actual reality. And for the escaping modes, there exists a corresponding set of modes, linked by quantum entanglement, that are trapped behind the event horizon. We can interpret those as corresponding to the swallowed antiparticle partner. So, the split matter, antimatter part of the popular picture is a reasonable heuristic. But there are reasons to be cautious about certain aspects of this simplified image. Firstly, this radiation isn't localized to a specific point. Remember, Hawking radiation has wavelengths the size of the event horizon, which means the size of the entire black hole. These are the de Broglie wavelengths of the created particles, and they tell us that there's an enormous quantum uncertainty in the precise location of these particles. Hawking radiation must appear to originate from the black hole globally, not from specific points on its event horizon. In fact, an observer in free fall, crossing the horizon, would perceive nothing unusual. To them, space is locally flat, and the vacuum should simply look like a vacuum. This radiation is visible only to distant observers. Well, there is one interesting exception. If you were to activate your jetpack and hover at a fixed distance, just above the horizon, then you would detect particles. You'd see what's known as Unruh radiation. We'll explore its fascinating relationship to Hawking radiation in a future discussion. By the way, Hawking radiation is primarily composed of photons and other massless particles. To produce particles with mass, the energy of the radiation would need to be high enough to cover the rest mass of that particle. So, it's generally okay to interpret the narrative of Hawking's calculation as the splitting of entangled matter and antimatter pairs. Even if it is largely a heuristic interpretation, it's the ultimate cause of this splitting that remains hard to precisely pin down. We can think about positive and negative frequency modes being mixed due to scattering, perhaps by the yet undiscovered graviton, the quantum particle of gravity. Other physicists have arrived at Hawking's result using very different, seemingly unrelated narratives. For example, in 2001, Parikh and Wilczek obtained the exact same thermal spectrum for Hawking radiation by considering particles escaping from beneath the event horizon through quantum tunneling. The common thread running through all these derivations is quantum uncertainty. For instance, uncertainty in position and momentum can lead to particle pairs that were once in the same location, or modes that were once on the same world line, becoming separated by the event horizon. Alternatively, uncertainty in energy can directly lead to particle creation. Whichever way you interpret it, it's incredibly difficult to avoid the conclusion that black holes actually emit particles. The fact that different derivations lead to exactly the same result, or that the radiation consistently looks thermal, cannot be a mere coincidence. It's remarkably hard to make Hawking radiation disappear in the mathematical framework, and believe me, Stephen Hawking himself initially tried to. Ultimately, however, these calculations are all clever approximations, albeit utterly brilliant ones. Without a complete quantum theory of gravity, the true origin of Hawking radiation will remain shrouded in mystery. And there are other mysteries we haven't even touched on yet. For example, what actually happens to the particles or quantum modes that are trapped by the black hole? How do they end up reducing the black hole's mass instead of increasing it? And then there's the famous information paradox, in which Hawking radiation appears to destroy what should be a conserved quantity, quantum information. We'll tackle all of these intricate questions in future episodes. For now, we must conclude that black holes do radiate, and in doing so, they slowly evaporate. The most frightening monsters of general relativity are ultimately unraveled by the brilliant mind of Stephen Hawking and a mysterious quirk of quantum spacetime. Black holes seem like they should possess no entropy at all. but in fact, they contain most of the entropy in the entire universe. Let's try to understand why this is. At first, it genuinely seemed that black holes were so simple, so featureless, that they shouldn't have any entropy. Yet, it turns out they actually hold the vast majority of the universe's entropy. Let's delve into why this is the case, because this profound fact might force us to conclude that the universe itself is a hologram. Black holes present a significant problem. They are the inevitable outcome of extreme gravitational collapse. At least, they are inevitable according to the equations of Einstein's general theory of relativity. That theory is one of the most rigorously tested in all of physics, which means we should probably trust in the existence of black holes. Furthermore, we've observed them through their powerful gravitational effects on surrounding space and through the gravitational waves produced when they merge. And yet, if black holes exist, which they apparently do, they seem to contradict other fundamental theories in physics that are just as sacred as general relativity. They cause all sorts of issues with quantum theory, which we've discussed before and will briefly review in a moment. But they also present an apparent conflict with the very notion of entropy and the second law of thermodynamics. It was while contemplating that very conflict that Jacob Bekenstein realized an incredible connection between black holes and thermodynamics. His groundbreaking insight launched an entirely new way of thinking about the universe in terms of information theory.